Hi everyone, welcome to another episode in Chapter 8, Lines and Planes, and today we'll be covering 8.5 Intersections of Lines and Planes. In three-dimensional space, there are three possibilities for the intersection of lines and planes with relation to their system of equations. The first possibility is the line intersects the plane at a point, therefore the system has one solution. The second possibility is the line lies directly on the plane and the system has an infinite number of solutions since all points of the line intersects with the plane. The third possibility is the line is parallel to the plane, therefore the system has no solution since the line does not intersect with the plane. The minimum distance represented by d between a point P and a plane can be found by using this equation. Distance equals the magnitude of the dot product between vector n and pq over the magnitude of vector n. Q is any point located on the plane, and n is the normal vector of the plane, where normal is defined as perpendicular to the surface of a plane. Here are some key terms to remember in this unit. Distinct. A line is parallel to and distinct from a plane when line and plane do not intersect. Coincident. A line is parallel to and coincident to a plane when they share a common point. Coplanar. Vectors are lines that are located in or parallel to the same plane. Skew lines. Two lines that lie on different planes do not intersect and are not parallel to each other, as shown in this diagram below.
This question asks if the following plane intersects with the following line and to state how many solutions there are. To find the intersection of the line and plane, we first take the direction vectors of the plane equation and take the cross product of both vectors. These vectors are m, 2, 1, negative 3, and n, negative 1, 2, and 1. Now the resultant cross product of these two vectors are x is equal to 7, y equal to 1, and z is equal to 5. Now that you have your a, b, and c values for the equation, now you only need to find the value of d. To do this, you plug in the position vector of x is equal to 1, y is equal to 3, and z is equal to negative 2 into the equation to find the value of d. And through this, the value of d is found to be equal to 0. And your final scalar equation for the plane is 7x plus y plus 5z is equal to 0 as d is 0. Now that you have the scalar equation for the plane, you can plug in the x, y, z values of your line equation to find if the line intersects with the plane. To do this, you first must add the x, y, and z values of the position and direction vectors within the line equation. After that, you plug in the resultant x, y, and z values into the scalar equation. If the resultant is 0, then it does intersect with the plane. If it is anything other than 0, then there's no intersection. So as of a result, this equation is negative 18, which is not equal to 0. So therefore, it doesn't intersect.
Okay, so for knowledge, one of the questions is state the solution to the system. And they give us a vector equation of a line, and they give us a equation of a plane. And they want to know where these two intersect. So the first step that I would do is I have these two written out. And I'll start by looking at the vector equation, and I want to simplify this and turn it into a group of parametric components. So I'll do that by looking at, so we have equals 6, 11, 1, and then plus, we'll just multiply the t, like multiply t to all of this, so it'll be plus t, 5t, and 2t, right? And then how we do it is it'd be equal to, so we would group like the first one here, there, and then the y, so 11 plus 5t, 1 plus 2t, like that. So 6 plus t, 11 plus 5t, 1 plus 2t. So we have these parametric components, as you can see. Sorry about the shakiness. And then this would be your x, y, and z, right? So now what we do here is we would sub this x, y, and z into our equation of the plane. So it would be now, instead of x, we would just write 6 plus t. It would be 6 plus t plus 6 plus t plus 6 plus t plus bracket that, sorry, plus 3, 11 plus 5t, and then plus 2, and then you sub in the z part, so 1 plus 2t, minus 1 equal to 0, so like that. So we sub x in here, y, and z into that equation. And now we'll simply just, we're just going to simplify it. So it's going to be 6 plus t plus 3 plus 15t plus 2 plus 4t minus 1 is equal to 0, like that. Then we're going to get 20t is equal to negative 40 when we simplify it. So it's going to be t is equal to negative 40 over 20. T is equal to negative 2. Just like that. Right? Once we get this, we simply sub this into wherever it says t for these parametric components, and we'll get a coordinate that where the line and the plane intersect. So it's 6 plus t, so instead we're gonna get 6 plus negative 2. So I just subbed in t into the parametric parts, and then from there it was it's just like that. Yeah, sub it in for t, and then you get this. This is your parametric component. You subbed it into the parametric component, and you get this point where the equation and the line and the plane intersect at this point, 4, 1, and negative 3.
This question is determine the distance between point P and the given plane. Point P is 1, -1, and 3, and the plane is 4x plus 6y minus 3z equals 4. So by definition, we know the distance equation is equal to the magnitude of the dot product between vector n and vector pq over the magnitude of vector n. So to solve for point Q, we're going to choose arbitrary values for x and y and solve for z by plugging them into our plane equation. Therefore, let x equals 4 and let y equals 0. So we end up with the final answer of z equals 2 over 3. So now let's write down our given. We have a direction vector which is represented with vector n, which is 4, 6, and -3. We have point Q, which is 4, 0, and 2 over 3. And we have point P, which is 1, -1, and 3. So now we're going to solve for vector PQ. To solve for vector PQ, we have to do point Q minus point P. So point Q is 4, 0, and 2 over 3. Point P is 1, -1, and 3. When we subtract point P from point Q, we'll get a final answer of 3, 1, and -7 over 3. So now since we have vector n and vector pq, we could sub them both into our distance equation to solve for the minimum distance. So on top, since we do the dot product between vector n and vector pq to find the magnitude, when we do that, we would get a final answer of 25. Then on the bottom, once we do the magnitude of vector n, we would get a final answer of root 61. Therefore, the distance between the point and the plane is 25 over root 61 units.
So the question that I'm doing says, write an equation of the plane that contains the point P, 2, -4, 1, and is parallel to the line 7, 3, -2, and t plus t, 1, -1, and 5. So first thing I did off the bat was I looked at this part of the equation and the point, and I looked at the resultant vector between there, so it would be -5, -7, and 1. And now what I'm going to do is I'm going to take the cross product to find the normal vector. And I'm going to do this by finding the cross between this component of the equation. So 1, -1, and 5. And I'm going to cross that with the part I got right here. So I'm going to cross it with -5, -7, and -1. And this, when I do it, it's going to give me the answer to this cross product is going to be 36, -24, and -12. Now from here, I'm going to use this as a basis of the equation of the plane. So it's going to be 36x minus 24y minus 12z. So let me just write that out. So it's going to become 36x minus 24y minus 12z. And I'm going to make it equal to d. And we're going to solve for d in order to get this equation of the line. So to solve for this, after this step, what we're going to do is we're going to sub back in this vector, the first part of the equation. So we're going to sub that in. So this would be x, y, and z. So we're going to sub in 36 times 7. 36 times 7 minus 24 times 3 minus 12 times -2 is equal to d, right? Sorry about that. Then from there, it's going to become 252 minus 72 plus 24 is equal to D. And this is going to simplify to 204 is equal to D. And that's it really. So now we have the equation of the plane that they were asking for. So the equation is going to be 36 x minus 24y minus 12z is equal to 204. So that's going to be our equation of the plane, the answer.
So this question asks, show that lines L1 and L2 are skew. So remember that skew lines are defined as two lines that are not parallel, do not intersect, and do not lie on the same. So to our right we have some conditions. Vector M1 and vector M2 can be defined as the direction vectors for each of the lines, and their cross product must equal vector n, which is the plane of the paper. Vector P1, P2 is the combined vector of line L1 and L2. And the dot product between vector P1, P2 and the cross product between vector M1 and M2 must equal 0 if the lines lie in the same plane. For this case, since we're proving that they're skew, they cannot equal 0 if the lines are skew. So we know vector M1 is 1, 2, and 0 from our first line, and vector M2 is -3, 0, and 1 from our second line. Therefore, by taking the cross product, we get a final vector of 2, -1, and 6. So now we're going to find vector P1, P2. To find vector P1, P2, we must subtract point P1 from point P2. Point P2 is -5, 5, and 6, and point P1 is 2, 5, and 4. Therefore, when we subtract point P1 from point P2, we get a final vector point P1, P2 of -7, 0, and 2. So now to check if these two lines are skew, we're going to see if the dot product between vector P1, P2 and the cross product between vector M1 and vector M2 equals 0. If they do not equal 0, that means that these two lines are skew. Since -2 does not equal 0 and the left-hand side does not equal the right-hand side, it is proven that these two lines are both skew. So part B reads, write the equation of plane pi1 that contains L1 and the equation of plane pi2 that contains L2 such that pi1 and pi2 are parallel. So now we're going to choose arbitrary coefficients for x, y, and z for both these equations and keep them constant since these two planes are parallel and the normal vectors must be parallel with each other. So we will choose 2, -1, and 6 correspondingly. So D represents our coefficient for each equation. So for equation 1, since it contains L1, we must sub our first point P1 into the equation 1. So since P1 is 2, 5, and 6, we must sub it into the equation to solve for D. When we sub into the equation, we get 23 equals D. Therefore, our first equation, pi1, is 2x minus y plus 6z minus 23 equals 0. Equation 2. Since it contains L2, we're going to sub our second point, P2, into the equation to solve for D. So P2 is -5, 5, and 6. So we sub that into the equation, we get 21 as D. Therefore, our equation number 2, pi2, is 2x minus y plus 6z minus 21 equals 0. We know that these two planes are parallel since the normal vectors are equal and parallel to each other since they both are 2, -1, and 6.
This problem states to write the equations of a line and a plane that intersect at the point -3, 5, and 2. As the point of intersection is -3, 5, and 2, you first plug in these values into a standard scalar plane equation, such as ax plus by plus cz plus d is equal to 0. Through this, you get -3a plus 5b plus 2c plus d is equal to 0. Now you can plug in any set of values for a, b, c, and d as long as the resultant is 0. These values will now create the plane equation, which is 2x plus 4y minus z is equal to 0. Now to find the equation that intersects the point, you get the x, y, and z values of the POI and set a value for t that will be in all equations equal to these values, such as t is equal to 2. Then you change the equation according to the fixed value of t to make it equal to the x, y, or z value. After that, the constants in each equation, which are -1, 1, and 0, will be the coordinates for the position vector in the equation, and the multiples of t in each one will be the x, y, and z values for the direction vector. Finally, those two vectors will be added to make the equation that intersects the plane. And now this is your final plane and line equation that will intersect the point of intersection.
So here are some practice problems along with the solutions, so feel free to pause the video, do the question, then revert to the solution afterwards. Thank you for listening to our video on Chapter 8.5, Intersections of Lines and Planes.